Above the early Earth, the atmosphere breathes in colors that no human eye will witness for billions of years to come. Methane drifts in amber-tinted layers through a sky that knows nothing of blue, while hydrogen sulfide paints the horizon in shades of rust and burnt copper. The planet spins beneath a sun that burns younger and dimmer than the star we know today, casting pale yellow light through gas mixtures that would poison any oxygen-breathing creature in seconds, yet somehow cradle the precise chemistry that will eventually give rise to consciousness itself, to eyes that can look up at stars and wonder about their origins. This is Earth during the Archean Eon, that vast stretch of time between 4 billion and 2.5 billion years ago, when the planet's surface temperature hovers dangerously close to the boiling point of water and the atmospheric pressure measures thick enough to crush modern life forms before they could attempt their first breath. The continents, such as they are, consist mainly of volcanic islands scattered across a global ocean that contains no free oxygen, no complex organic molecules, no hint of the biological revolution that will eventually transform both sea and sky into something recognizably terrestrial. Yet even in this seemingly hostile world, cosmic visitors arrive with the same gentle persistence they demonstrate today. The same patient regularity they will maintain throughout Earth's entire geological history. Each dawn brings its measured quota of interstellar dust, microscopic fragments of distant stellar explosions, and, occasionally, larger messengers that carry within their crystalline structures stories from the deep spaces between stars. Narratives written in isotopic ratios and rare element concentrations that preserve the conditions under which they formed in stellar nurseries that ceased to exist long before our solar system began to condense from its own cloud of gas and dust. The cosmic rain falls continuously, silently, measurably, with a consistency that rivals the most reliable geological processes. Modern calculations, based on satellite observations and atmospheric sampling, suggest that Earth receives approximately 40,000 tons of extraterrestrial material each year. Though during the planet's violent youth, when the solar system contained far more debris and the gravitational influences that sweep space clean had not yet established their current patterns, this figure was likely many times higher. Most of this material arrives as particles smaller than the period at the end of this sentence, fragments chipped from asteroids during ancient collisions, traces of cometary ice that sublimated and refroze countless times during million-year journeys through the outer solar system, and dust grains that formed in the stellar winds of dying red giants located hundreds or even thousands of light-years away. These particles drift down through the thick Archean atmosphere like snow falling through honey, their descent slowed by air so dense that each grain takes months to complete its final approach to the surface, while chemical reactions powered by ultraviolet radiation alter their outer layers in ways that both destroy and preserve evidence of their interstellar origins. Some grains melt completely during their passage through the atmosphere, contributing their atoms to the growing inventory of elements available for Earth's ongoing chemical experiments. Others survive the journey intact, carrying within their mineral matrices information about stellar processes, galactic chemistry, and cosmic events that occurred when the universe itself was younger and the heavy elements necessary for rocky planets existed in far smaller quantities than they do today. The early Earth accepts these gifts with the same geological indifference it shows toward its own violent internal processes, somewhere far beneath the planet's surface. Convection currents churn magma through chambers the size of modern cities, while massive plumes of molten rock rise toward the crust like slow-motion explosions that take millions of years to complete their ascent. Volcanic eruptions paint the sky with ash and sulfur compounds, while in the darkness above, invisible against the methane haze, a grain of cosmic dust no larger than a virus carries within its crystalline structure the isotopic signature of a supernova that exploded when the Milky Way galaxy was younger and less chemically mature. when our solar system existed only as a vague gravitational tendency within a much larger molecular cloud that had not yet begun to collapse under its own weight. Only took 4.5 billion years for this particular collection of atoms to find their way here, riding solar winds and gravitational currents across distances so vast that light itself, traveling at 300 million meters per second, the fastest speed possible in this universe, requires centuries or millennia to traverse the space between their stellar origin and their terrestrial destination. Such patience deserves recognition. Some acknowledgement of the cosmic coincidences that brought these specific atoms together at this specific moment in Earth's history. Yet the planet offers none. No consciousness yet exists to marvel at these intersections of space and time. No intelligence to wonder about the stories preserved within mineral lattices that remember the exact temperature and pressure conditions of stellar cores that ceased to exist before Earth's oldest surviving rocks began their slow crystallization from pools of cooling magma. Scientists working today with the most sophisticated analytical instruments ever constructed can detect trace amounts of material from thousands of different stellar sources scattered throughout Earth's crust, dissolved in its oceans, and suspended in its atmosphere. Each mountain range contains atoms that formed in different types of stars. The calcium in limestone cliffs originated in the nuclear furnaces of massive stars that burned bright and died young, while the iron ore deposits that powered human civilization formed in the final moments of stellar collapse, when gravitational forces compressed atomic nuclei beyond their normal limits and created elements that cannot form under any other conditions in the known universe. Every handful of soil represents a library of cosmic events written in languages of rare earth elements and noble gas isotopes, chemical signatures that preserve information about stellar nucleosynthesis, supernova explosions, and the gradual enrichment of interstellar gas clouds with the heavy elements necessary for rocky planet formation. The Pacific Ocean holds dissolved metals that originated in stellar nurseries located on the opposite side of the galaxy, while the iron currently circulating in human blood carries the chemical signature of supernovae that exploded billions of years before the first bacterial cells learned to harness sunlight for energy, before the first complex molecules began their patient experiments with self-replication and heredity. Yet during the Archean Eon, no awareness exists to read these signatures, no intelligence capable of piecing together the remarkable story of how Earth's surface serves as an inadvertent archive of galactic chemical evolution. The planet simply accumulates these cosmic contributions with the same methodical persistence it demonstrates in building continents and eroding mountain ranges, adding layer upon layer of extraterrestrial material to a geological record that will eventually span billions of years and preserve evidence of cosmic processes that occurred throughout the galaxy's long history of star formation and stellar death. The mystery that haunts modern astrobiologists and planetary scientists centers not on whether cosmic material arrives on Earth. This much the isotopic evidence makes abundantly and unquestionably clear, but on how significantly these constant, gentle contributions from elsewhere may have influenced Earth's early chemical evolution and the eventual emergence of life itself. Some researchers, working with sophisticated models of early atmospheric chemistry and cosmic dust delivery rates, calculate that the organic molecules necessary for life's emergence may have arrived through this cosmic delivery system, carried within the ice of comets that formed in the outer regions of other stellar systems, or locked within the carbon-rich matrices of meteorites that condensed from the debris of stellar explosions and spent millions of years drifting through interstellar space before gravitational forces guided them into our solar system. Other scientists argue with equal conviction that Earth's own volcanic and atmospheric processes were entirely sufficient to generate life's precursor molecules, that the complex chemistry of biological emergence needed no interstellar assistance to develop from purely terrestrial ingredients. They point to laboratory experiments that demonstrate how simple organic compounds can form spontaneously under conditions similar to those that existed on the early Earth. How lightning and ultraviolet radiation can drive chemical reactions that produce amino acids and other biological building blocks from nothing more than water, methane, and ammonia. The debate continues in laboratories and conference rooms around the world, fueled by new discoveries in meteorite analysis and advances in our understanding of how organic chemistry behaves under extreme conditions. While the planet itself remains characteristically indifferent to both theories and all the human speculation they generate. Above the methane-rich Archean atmosphere, space continues to be what it has always been, mostly empty, occasionally punctuated by visitors whose origins encode stories that no intelligence is yet present to decipher, messages written in atomic structures and isotopic ratios that will wait billions of years for conscious minds capable of reading their cosmic significance. Somewhere in the darkness, beyond the solar system's edge, other objects have already begun journeys that will not conclude for millions of years, following trajectories determined by gravitational influences so subtle and long-range that they operate on temporal scales that make the formation and erosion of entire mountain ranges appear sudden by comparison. The universe practices patience on levels that even geology finds impressive, delivering its messages across distances and time periods that dwarf human comprehension, yet somehow managing to arrive precisely when and where they are needed to become part of Earth's slowly evolving story. In the darkness beyond Neptune's orbit, where sunlight arrives so weakened that noon resembles the faintest twilight on Earth, a vast spherical shell of ice and rock drifts through the cosmic cold with a patience that makes geological time seem hurried by comparison. The Oort cloud extends from roughly 2,000 times Earth's distance from the Sun to nearly halfway to Proxima Centauri, our nearest stellar neighbor, encompassing a region so immense that light itself, traveling at 300 million meters per second, requires over a year to cross from the cloud's inner boundary to its outermost edge, where the Sun's gravitational influence begins to compete with the pull of nearby stars for control over these distant wanderers. Here, in this realm of perpetual winter, temperatures hover just a few degrees above absolute zero, so cold that the motion of individual atoms slows to barely perceptible vibrations, so remote that the Sun appears as nothing more than an unusually bright star among the thousands visible in the perpetual night. Earth, if it could be seen at all from these distances, would appear as an invisible speck orbiting an ordinary star, indistinguishable from countless other stellar systems scattered throughout the galaxy's spiral arms. Yet this seemingly empty region contains some of the most important archives of early solar system history, frozen libraries that preserve chemical information about conditions that existed when the planets themselves were nothing more than vague condensations within a disk of gas and dust. This is where comets are born, not in the violent heat of stellar formation or the chaotic collisions that characterize the inner solar system, but in the patient, almost reverent accumulation of ice and dust that occurs when temperatures drop low enough for water vapor to crystallize around microscopic grains of cosmic debris. The process unfolds with a slowness that makes continental drift appear sudden. Individual particles, each no larger than a bacterium, drift toward each other under gravitational influences so weak that millions of years pass before collections of ice crystals grow large enough to be called snowballs, and millions more before these snowballs merge through countless gentle collisions into objects substantial enough to survive the eventual journey inward toward the Sun's warmth. Each comet nucleus that forms in these distant reaches carries within its frozen structure a chemical record more detailed and pristine than any geological formation on Earth. Water ice preserves traces of the isotopic ratios that characterize the original stellar nebula from which our entire solar system condensed, while frozen carbon dioxide and methane lock away organic molecules that formed in the same primordial environment that gave rise to Earth and its neighboring worlds. These molecules remain virtually unchanged by the billions of years that have passed since their formation, protected by temperatures so low that chemical reactions essentially cease, creating natural time capsules that preserve conditions from an era when the Sun was still adjusting its nuclear furnace and the planets existed only as probability clouds within a vast disk of debris. Only took 50 million years or so for these distant regions to cool sufficiently for large-scale ice formation to begin, practically instantaneous by cosmic standards, though long enough for entire mountain ranges to rise and erode away on any world where such geological processes might occur. During this cooling period, the young solar system underwent dramatic changes as the giant planets migrated outward from their original formation zones, their gravitational influences reshaping the distribution of smaller objects throughout the entire system and establishing the orbital patterns that persist to this day. The Oort cloud contains an estimated 1 trillion individual objects, ranging from house-sized chunks of dirty ice to mountain-sized agglomerations of frozen gases and rocky debris, all scattered through a volume of space so vast that the average distance between neighbors measures several times the span between Earth and Sun. They follow orbits so elongated and eccentric that some take millions of years to complete a single circuit around the solar system's center of mass, following paths that carry them from the realm where interstellar space begins to the inner solar system and back again in journeys that span geological ages and witness the rise and fall of entire biological epochs on any planets that might exist within their gravitational domain. The mathematical elegance of these orbital patterns reflects the fundamental physics that governs all gravitational systems, from the smallest asteroid to the largest galaxy cluster. Each comet follows an elliptical path determined by its velocity and position at the moment when gravitational forces last significantly altered its trajectory, whether through interaction with a passing star, the influence of galactic tidal forces, or the long-term perturbations caused by the slow precession of the solar system's orbit around the galactic center. These trajectories can remain stable for millions of years, then change dramatically when subtle gravitational influences accumulate beyond a critical threshold, sending previously stable objects on new paths that may carry them into the inner solar system or eject them entirely into interstellar space. Scientists working with the most sophisticated computer models estimate that the Oort cloud formed through a complex process of gravitational scattering that occurred during the early solar system's most chaotic period, roughly 4.5 billion years ago, when the giant planets were still migrating outward from their formation zones closer to the Sun, and their gravitational influences flung countless smaller objects onto trajectories that carried them far beyond the orbits of what would eventually become the known planets. Jupiter and Saturn, in particular, acted as cosmic billiard balls, using their massive gravitational fields to redirect icy bodies that originally formed in the region between Mars and Jupiter onto elliptical orbits that extended thousands of times farther from the Sun than their original circular paths. This scattering process was remarkably efficient. Computer simulations suggest that for every comet nucleus that settled into a stable Oort cloud orbit, dozens of others were ejected entirely from the solar system, becoming interstellar wanderers that now drift through the galaxy carrying chemical signatures of our solar system's formation. These exiled objects represent a form of cosmic diaspora, spreading the isotopic and molecular fingerprints of our stellar neighborhood throughout nearby regions of the galaxy, where they may eventually encounter other stellar systems and contribute their ancient chemistry to entirely different planetary formation processes. The mystery that puzzles modern astronomers involves understanding exactly how this scattering process unfolded and whether it occurred gradually over millions of years through countless small gravitational nudges, or in sudden, dramatic bursts triggered by close encounters with passing stars, or the gravitational influence of the galaxy's spiral density waves. Current evidence suggests that both mechanisms likely played important roles, but the precise details remain elusive. Hidden in the complex mathematics of multi-body gravitational systems that challenge even the most powerful supercomputers and require observational data that spans timescales far longer than human civilization has existed. What remains abundantly clear from both theoretical calculations and direct observations is that these distant ice balls represent some of the most pristine and chemically unmodified material in the entire solar system. Natural time capsules that preserve conditions from the era when planets were forming and the sun was still surrounded by the disk of gas and dust from which all solid objects in the solar system eventually condensed. Unlike the rocky planets, which have been thoroughly processed and reprocessed by billions of years of geological activity, volcanic eruptions, plate tectonics, atmospheric weathering, and biological processes, or the gas giants, whose atmospheric compositions have been continually altered by ongoing circulation patterns and internal heat generation. Comets retain their original chemical signatures with minimal modification. The ice that comprises the bulk of comet nuclei formed directly from the same water vapor that existed in the original solar nebula, while the rocky and metallic components represent dust grains that condensed from stellar atmospheres and supernova ejecta billions of years before our solar system began to form. Spectroscopic analysis of comet tails reveals the presence of organic molecules that could only have formed under the specific temperature and pressure conditions that characterize the early solar nebula, providing direct evidence of the chemical processes that preceded and enabled planetary formation. When gravitational perturbations occasionally nudge one of these frozen wanderers onto a trajectory that brings it closer to the sun, a process that typically requires the combined gravitational influence of passing stars, galactic tidal forces, and the long-term orbital evolution of the giant planets, the resulting spectacle provides Earthbound observers with a direct glimpse of primordial solar system material that has remained essentially unchanged for billions of years. As the comet approaches the inner solar system and begins to feel the sun's warmth for the first time in its existence, ice begins to sublimate directly from solid to vapor, creating the characteristic tail that can stretch millions of kilometers through space and become visible from Earth despite originating from objects no larger than small cities. This sublimation process represents a visible manifestation of the same chemical transformations that occurred throughout the early solar system during its formation, now playing out in slow motion across the span of years rather than the millennia over which planetary accretion originally unfolded. The gas and dust released from the comet's nucleus carry isotopic signatures that reveal details about stellar nucleosynthesis processes that occurred in previous generations of stars, while organic molecules locked within the ice provide clues about the prebiotic chemistry that may have contributed to the emergence of life on Earth and possibly other worlds. Yet for every comet that makes this spectacular journey toward the inner solar system, millions more remain in their distant orbits, circling the sun at distances so great that they receive virtually no warmth from our star and experience gravitational influences from nearby stars that can be stronger than the sun's own pull. These objects exist in a state of cosmic hibernation, their internal chemical processes essentially stopped by the extreme cold, their orbital periods so long that they have completed only a handful of circuits around the sun since the solar system formed. The universe practices such extraordinary patience in these outer reaches, where time moves according to rhythms that dwarf human comprehension and make even geological processes appear hurried. A single orbit around the sun can take longer than the entire evolutionary history of complex life on Earth, while the ice that comprises these distant objects remains virtually unchanged since the epoch when Earth itself was nothing more than a loose collection of rocky fragments slowly spiraling toward each other through gravitational attraction within the disk of debris that surrounded the young sun. Stars do not maintain polite distances from each other throughout the galaxy's long, stately rotation around its central supermassive black hole. Every few million years, sometimes more frequently during the solar system's passage through the galaxy's spiral arms, where stellar densities increase dramatically, One of these distant suns passes close enough to our local gravitational domain to disturb the delicate orbital balance that has held the Oort cloud's trillion icy wanderers in their patient, millennia-spanning circuits around the Sun. These stellar encounters occur with the same geological inevitability as continental drift, or the slow rise of mountain ranges, gradually, predictably according to the laws of celestial mechanics, yet with consequences that ripple through the solar system's outer reaches for millions of years after the visiting star has continued on its journey through the galactic disk toward whatever stellar destiny awaits in the spiral arms ahead. The mathematics governing these cosmic interactions unfolds according to gravitational principles that Isaac Newton first described in the 17th century. Elegant differential equations that seem deceptively simple when written on paper, yet generate behaviors of extraordinary complexity when applied to systems containing trillions of individual objects scattered across volumes of space measured in light years. The complexity emerges not from any fundamental mystery in the underlying physics. Gravity follows well-understood mathematical laws that can be expressed in a handful of equations, but from the sheer number of gravitational relationships involved and the vast timescales over which even microscopic influences accumulate into dramatic transformations of orbital geometry, energy distribution, and the ultimate fate of objects that have circled the Sun since the solar system's earliest epochs. A star passing within a few light years of our solar system, close enough that its light would appear noticeably brighter than background stars if observed from Earth, yet still separated by distances that electromagnetic radiation itself requires multiple years to traverse at the universe's maximum possible speed, exerts gravitational forces on individual Oort cloud objects that are individually so weak as to be nearly unmeasurable by any conceivable instrument, yet collectively powerful enough to reshape the entire population's orbital characteristics over periods spanning geological ages. Comets that have maintained essentially stable orbits for billions of years, following elliptical paths so elongated that their orbital periods exceed the entire evolutionary history of complex life on Earth, suddenly find their trajectories altered by infinitesimal velocity changes that compound over millennia into dramatic modifications of direction, orbital period, eccentricity, and ultimate destiny within or beyond the solar system's gravitational boundary. The most recent significant stellar encounter that astronomers have identified and analyzed in exhaustive detail occurred roughly 70,000 years ago. During the late Pleistocene epoch, when Earth's surface supported Neanderthal populations throughout Europe, and early modern humans were beginning their epochal migration from Africa across the continents that would eventually harbor every major human civilization. A red dwarf star designated Schultz's star in astronomical catalogs, accompanied by a brown dwarf companion that barely qualifies as a stellar object under current astrophysical definitions, approached within approximately 1 light-year of the Sun, close enough that its gravitational influence penetrated deep into the Oort cloud's outermost regions and nudged thousands upon thousands of icy objects onto new trajectories that range from gentle orbital modifications to complete ejection from the solar system into the interstellar void. Astronomers working with sophisticated computer models that simulate gravitational interactions across millions of years have calculated that comets disturbed by this ancient stellar passage are still arriving in the inner solar system today, their extraordinarily long elliptical orbits only now bringing them close enough to the Sun for ice sublimation to begin in earnest, for their surfaces to warm sufficiently to release the gases and dust that create the spectacular tails visible from Earth, and for their presence to become detectable through the telescopic observations and spectroscopic analyses that allow modern science to piece together their cosmic histories and decode the chemical information they carry from the solar system's formation era. These objects carry within their frozen nuclei detailed chemical information that dates back 4.5 billion years to the solar system's formation, isotopic signatures that preserve precise details about stellar nucleosynthesis processes that occurred in previous generations of stars before our Sun began its own nuclear burning. Organic molecules that formed under temperature and pressure conditions that no longer exist anywhere in the known solar system, and trace elements that provide direct evidence of supernova explosions that enrich the interstellar medium with heavy elements necessary for rocky planet formation. Only took 70 millennia for these particular cosmic messengers to complete their journey from the distant, frigid outer reaches of solar space to Earth's warm, life-bearing neighborhood, a brief interval by the standards of cosmic evolution and stellar dynamics. Yet long enough for human civilization to emerge from scattered hunter-gatherer communities organized around seasonal migration patterns and subsistence strategies to the technologically sophisticated, globally interconnected society that can now detect and analyze these ancient visitors with instruments sensitive enough to identify individual molecular species within comet nuclei and determine their isotopic compositions with precision that would have seemed impossible to scientists working just decades ago. The temporal irony resonates through astronomical conferences and peer-reviewed research papers, where scientists discuss objects that began their current inward journey tens of thousands of years before humans developed agriculture, invented writing systems, constructed permanent settlements, or conceived of the scientific method as a systematic approach to understanding natural phenomena, yet arrive precisely during the narrow historical window when our species has developed the theoretical understanding and technological capabilities necessary to read their chemical signatures and decode the stories of stellar formation, galactic chemical evolution, and solar system dynamics that these frozen time capsules have preserved throughout their long exile in the cosmic cold beyond the reach of solar warmth. When a passing star's gravitational field reaches into the Oort cloud, it preferentially affects objects whose current orbital orientations happen to align with the direction and timing of the stellar encounter, creating complex selection effects that depend on the three-dimensional geometry of orbital mechanics and the precise velocity vectors of both the visiting star and the diverse comet populations it encounters during its passage through our solar system's outer regions. These gravitational interactions produce remarkably diverse outcomes depending on subtle differences in initial conditions that can only be calculated accurately using sophisticated numerical simulations that model the motion of millions of individual objects over time, scales spanning millions of years, and account for the cumulative effects of countless small perturbations. Some comets receive velocity increases that push them onto highly elliptical trajectories leading toward the inner solar system, where they will eventually approach close enough to the Sun for their icy surfaces to begin sublimating at detectable rates, creating the spectacular gas and dust tails that make them visible from Earth and provide opportunities for detailed spectroscopic analysis that reveals their chemical compositions, internal structures, rotational characteristics, and evolutionary histories preserved within crystalline matrices that have remained frozen since the solar system's youth. Others experience velocity decreases that cause their previously stable, nearly circular orbits to decay inward more gradually, creating a steady background rate of comet arrivals that persists for millions of years after the original stellar encounter, like cosmic echoes that continue long after the gravitational event that triggered them has faded into galactic history. Still, other objects receive gravitational kicks that increase their orbital energy beyond the solar system's escape velocity, transforming them instantly from solar system objects with well-defined orbital periods and predictable future positions into interstellar wanderers that will spend the remainder of their existence drifting through the galaxy's spiral arms, carrying with them chemical signatures and isotopic ratios characteristic of our solar system's formation, processes that may eventually reach other stellar systems and contribute their ancient molecular inventory to entirely different planetary formation episodes occurring around distant stars millions of years in the future. Computer models incorporating data from the European Space Agency's Gaia mission suggests that our solar system's current position within the Milky Way's disk places it in a region where significant stellar encounters occur roughly once every few million years on average, but this frequency varies considerably depending on the solar system's location relative to the galaxy's spiral arms, which contain higher concentrations of massive stars that can produce more dramatic gravitational disturbances when they pass through our solar system's vicinity during their own orbital motions around the galactic center. Galactic archaeology reveals that our solar system has experienced hundreds or perhaps thousands of significant stellar encounters since its formation 4.5 billion years ago, each leaving its gravitational signature encoded in the Oort cloud's current structure, creating subtle but persistent patterns in the distribution of comet orbital orientations, eccentricities, inclinations, and energy levels that persist long after the perturbing star has moved on to other regions of the galaxy. These orbital patterns provide a form of gravitational fossil record written in the language of celestial mechanics, allowing astronomers to work backward through time and reconstruct not only the solar system's detailed history of encounters with other stars, but also how our local stellar neighborhood has evolved over cosmic time. The chemical and biological consequences of these stellar encounters extend far beyond the realm of pure orbital mechanics into interdisciplinary questions that touch on planetary science, atmospheric evolution, geochemistry, and astrobiology. When stellar passages send showers of comets toward the inner solar system over periods spanning millions of years, they dramatically increase the rate at which pristine outer solar system material arrives at Earth and other terrestrial planets, where it can influence atmospheric composition, ocean chemistry, and potentially biological evolution through mechanisms that scientists are only beginning to understand. During periods of heavy comet bombardment triggered by stellar encounters, Earth's atmosphere and oceans receive enhanced doses of extraterrestrial water that carries isotopic signatures measurably different from terrestrial water sources. Organic molecules that formed under the unique temperature and pressure conditions that characterize the outer solar nebula billions of years ago, and rare isotopes that provide direct evidence of stellar nucleosynthesis processes that occurred in previous generations of stars before our solar system formed. Some researchers working at the intersection of astronomy, geology, and biology have calculated that these periodic comet showers may have played crucial roles in Earth's biological evolution, delivering pulses of prebiotic chemistry that supplemented terrestrial sources of organic molecules during critical periods when life was first emerging from purely chemical systems, or providing the additional water necessary to maintain stable oceans during episodes when the planet's internal geological processes might otherwise have allowed liquid water to disappear from Earth's surface. Currently, astronomers engaged in long-term stellar motion studies have identified several stars whose calculated trajectories will carry them close enough to our solar system within the next few million years to trigger significant Oort cloud disturbances comparable to or exceeding those caused by past encounters. These future stellar passages will initiate new episodes of enhanced comet bombardment, sending fresh populations of pristine outer solar system material toward Earth's orbital region millions of years from now, when human civilization, if it persists, may have access to analytical instruments and theoretical understanding that make our current astronomical achievements appear primitive by comparison. The universe maintains its own vast, unhurried schedule for these cosmic events, operating according to gravitational principles and galactic dynamics that remain utterly indifferent to biological convenience, technological readiness, or any consciousness that might exist to observe and attempt to understand these processes that connect individual stellar systems to the larger rhythms of galactic evolution. October 19, 2017 marks the moment when humanity first definitively recognized that something from beyond our solar system had arrived within the gravitational embrace of the Sun, crossing the invisible boundary that separates our local stellar neighborhood from the vast interstellar spaces that stretch between stars. The object, initially catalogued with the mundane designation C2017U1, and later given the more evocative name Oumuamua, a Hawaiian word meaning scout or messenger from afar arriving first, appeared in the data streams of the Panoramic Survey Telescope and Rapid Response System perched on the volcanic slopes of Haleakala in Hawaii as nothing more than a faint point of light moving against the background stars with a velocity and trajectory that immediately distinguished it from every other known object in the solar system's carefully catalogued inventory. The discovery emerged from the patient digital archaeology that characterizes modern astronomy, a process where sophisticated computers sift through thousands of CCD images each night, automatically identifying objects that move between successive photographs taken minutes or hours apart and calculating their orbital characteristics with mathematical precision that would have astounded astronomers working with photographic plates just decades earlier. The software algorithms that flagged Oumuamua for human attention recognized something unusual in its motion, a hyperbolic trajectory that curved through the inner solar system too quickly and at too steep an angle to represent any object bound by the sun's gravity in a closed, repeating orbit. Oumuamua's motion revealed an orbital eccentricity significantly greater than unity, the mathematical threshold that separates objects gravitationally bound to the solar system from those merely passing through on their way to other destinations in the galaxy. This clear signature indicated that the visitor originated somewhere beyond the sun's gravitational dominion and would eventually return to the interstellar medium from which it came, carrying with it whatever chemical and structural information it had acquired during its brief passage through our planetary neighborhood, like a cosmic bottle cast into the galactic ocean containing messages written in the language of isotopic ratios and crystalline structures. Only took a few days of follow-up observations from telescopes around the world for astronomers to recognize that they were witnessing something unprecedented in the history of telescopic astronomy. Previous comets and asteroids, no matter how exotic their compositions or unusual their orbital characteristics, had invariably proven to be native products of solar system formation processes, objects that condensed from the same primordial disk of gas and dust that gave rise to the planets billions of years ago and have spent the intervening eons circling the sun in predictable patterns governed by Newtonian mechanics. Oumuamua represented something entirely different, a tangible sample of material that formed around a different star, in a different stellar system, under physical and chemical conditions that could previously only be inferred from theoretical models of stellar evolution and spectroscopic observations of distant objects whose light had traveled for years to reach terrestrial telescopes. Here was direct, physical evidence that material can and does travel between stellar systems, bringing with it chemical information about stellar nucleosynthesis processes, planetary formation mechanisms, and the physical conditions that characterized entirely different cosmic environments. The international observational campaign that followed Oumuamua's discovery represented one of the most intensive efforts in modern astronomy, involving dozens of telescopes around the world working in carefully orchestrated shifts to maximize the brief window of opportunity for detailed study. As the object continued its hyperbolic trajectory away from the sun, moving at speeds approaching 30 kilometers per second relative to our solar system's center of mass, it grew steadily fainter and more difficult to observe with each passing day, creating intense pressure on the global astronomical community to extract as much scientific information as possible before it faded beyond detection limits. Astronomers measured its light curve with unprecedented precision to determine its rotation period and infer its three-dimensional shape, discovering that Oumuamua tumbles through space in a complex rotational pattern that suggests an elongated geometry unlike the roughly spherical shapes typical of most asteroids and comet nuclei. They analyzed its spectrum across multiple wavelengths to understand its surface composition, Finding that its reflective properties most closely resemble certain types of metallic asteroids, but with subtle differences that hint at a formation environment unlike anything found in our local planetary system. Most importantly, they tracked its motion with sufficient precision to detect subtle deviations from the purely gravitational trajectory that would be expected for an inert object following Kepler's laws. Measurements that required accounting for the gravitational influences of all the major planets and even the radiation pressure exerted by sunlight itself. These precise astrometric observations revealed one of the most puzzling aspects of Oumuamua's behavior and the source of ongoing scientific controversy about its nature and origins. The mystery that emerged from these painstaking measurements proved more intriguing than anyone had anticipated. Oumuamua appeared to be accelerating away from the Sun at a rate slightly but measurably greater than could be explained by gravitational forces alone, exhibiting what astronomers term non-gravitational acceleration, a phenomenon typically associated with cometary outgassing as water ice and other volatile compounds sublime directly from solid to vapor phase when heated by solar radiation and create a subtle rocket-like effect that can measurably alter an object's trajectory over time. Yet Oumuamua showed no signs whatsoever of the gas and dust emission that characterizes active comets during their approach to and retreat from the Sun's warming influence. No visible tail streamed behind it. No diffuse coma of sublimated gases surrounded its nucleus, and no spectroscopic signatures indicated the presence of water vapor, carbon dioxide, or other common cometary volatiles being released from its surface as it passed through the inner solar system. The object appeared essentially inert from an observational standpoint, yet continued to exhibit the non-gravitational acceleration that suggested some form of mass ejection or momentum transfer was occurring. This apparent contradiction, measurable non-gravitational acceleration without detectable outgassing, created a scientific puzzle that continues to generate intense debate years after Oumuamua disappeared beyond the reach of terrestrial telescopes. The absence of visible cometary activity, while simultaneously exhibiting behavior consistent with volatile sublimation, challenges conventional understanding of how comets behave and what physical processes can produce measurable changes in celestial object trajectories. Some researchers have proposed that Oumuamua consists of materials with properties unlike anything commonly found in solar system objects, perhaps composed primarily of solid nitrogen ice that would sublime at relatively low temperatures without producing easily detectable gases, or constructed with an internal structure characterized by subsurface voids that allow outgassing to occur through mechanisms not typically observed in conventional cometary nuclei. These models require that Oumuamua formed under conditions significantly different from those that characterized our solar system's early evolution, possibly around a star with different metallicity or evolutionary history. Other scientists have suggested more exotic explanations involving highly unusual geometric shapes that could experience radiation pressure effects strong enough to produce the observed acceleration. Surface properties that interact with solar radiation in unexpected ways, or even artificial origins that could account for the observed behavior without requiring conventional cometary processes. While these hypotheses remain speculative, they illustrate how Oumuamua's anomalous properties challenge existing theoretical frameworks and push the boundaries of scientific understanding about what types of objects can exist in the galaxy. The broader significance of Oumuamua's visit extends beyond the specific puzzles posed by its unusual characteristics to fundamental questions about the frequency of interstellar objects passing through our solar system. Statistical calculations based on Oumuamua's discovery suggest that similar objects transit through the inner solar system regularly, perhaps several times per year, but remain undetected because they are too small, too dark, or move too quickly to be identified by current astronomical surveys. The recognition that interstellar visitors arrive with measurable frequency has profound implications for understanding how material exchanges between stellar systems over cosmic time, how organic molecules might spread throughout the galaxy, and whether the chemical inventory available for planet formation includes contributions from multiple stellar environments. If objects like Oumuamua represent typical examples of interstellar debris, then every stellar system may periodically receive chemical contributions from its galactic neighbors, creating a form of cosmic recycling that could influence planetary formation and atmospheric evolution throughout the Milky Way. The isotopic and chemical signatures that Oumuamua carries, information that could only be partially extracted during its brief visibility, represent a direct sample of material that formed under different stellar conditions. Every measurement of its composition and behavior provides constraints on stellar evolution models, planetary formation mechanisms, and the range of physical conditions that existed in whatever stellar system gave birth to this wandering fragment millions of years ago. The realization that objects like Oumuamua exist in detectable numbers has fundamentally transformed astronomical observational strategies and theoretical expectations. Sky surveys originally designed to detect potentially hazardous near-Earth asteroids now maintain heightened awareness for objects with unusual orbital characteristics that might indicate interstellar origins, while theoretical models must account for the possibility that material exchange between stellar systems occurs more frequently than previously imagined. The profound irony embedded in Oumuamua's discovery reflects the serendipitous nature of astronomical research, where systematic surveys designed for one purpose, cataloging potentially dangerous near-Earth objects, occasionally reveal entirely unexpected phenomena that challenge fundamental assumptions about cosmic processes. The same telescopes and detection algorithms that scan the sky for homegrown threats have inadvertently opened an entirely new window into galactic archaeology, providing direct access to physical samples from other stellar systems. Future interstellar visitors, which statistical projections suggest should be detected with increasing frequency as surveys become more sensitive, will provide additional opportunities to study material that originated in different stellar environments and traveled for millions of years through interstellar space before arriving within range of terrestrial telescopes. Each such object represents a natural space probe carrying chemical information that would otherwise require interstellar travel to obtain. Delivering samples of distant stellar processes directly to our observational capabilities through the patient mechanics of galactic dynamics that operate on scales of space and time that dwarf human experience, yet somehow conspire to bring these cosmic messengers within reach of human curiosity. 3 years after Oumuamua's dramatic passage through the inner solar system, another interstellar visitor announced its presence in our celestial neighborhood, this time with enough advance warning to allow unprecedented observational preparation. Comet 2 I/Borisov, discovered by Crimean amateur astronomer Gennady Borisov on August 30th, 2019, while still beyond the orbit of Jupiter, provided the astronomical community with their first opportunity to study an active interstellar comet during its approach to the Sun, rather than catching brief glimpses of a rapidly departing object already fading into the cosmic distance, unlike its predecessor, which had revealed its interstellar origins only after careful orbital analysis. Borisov immediately displayed the unmistakable characteristics of a comet, a diffuse coma of gas and dust surrounding a central nucleus. Clear evidence of volatile sublimation occurring as solar heating began to warm its surface, even at distances where Earth receives barely 1% of the sunlight that illuminates our planet. The comet's hyperbolic trajectory and obvious cometary activity created an unprecedented scientific opportunity to study fresh material from another stellar system while it remained active and observable over a period of months rather than days. The observational campaign that followed Borisov's discovery surpassed even the intensive effort devoted to Oumuamua, involving space-based telescopes, ground-based observatories equipped with the most sensitive spectrographs, and coordinated timing that maximized data collection during the comet's relatively brief passage through the inner solar system. As Borisov approached its closest point to the Sun in early December 2019, instruments capable of detecting individual molecular species within its coma and tail analyzed the chemical composition of material that had potentially traveled for millions of years through interstellar space before arriving within range of terrestrial observation. The chemical fingerprints revealed by spectroscopic analysis told a story that was simultaneously familiar and profoundly alien. Borisov's coma contained water vapor, carbon monoxide, and other molecules commonly found in solar system comets, suggesting that the basic chemistry of ice formation and volatile compound behavior operate similarly in different stellar environments. Yet subtle differences in isotopic ratios and molecular abundances hinted at formation conditions unlike those that characterized our solar system's birth, providing direct evidence that stellar nucleosynthesis processes in Borisov's parent system had produced slightly different chemical signatures than those preserved in our local cometary population. Only took careful analysis of these spectroscopic measurements for researchers to recognize that they were examining material whose isotopic composition reflected the specific stellar evolution history of whatever star system had given birth to this wandering ice ball millions of years earlier. The ratio of carbon-12 to carbon-13 isotopes differed measurably from solar system values, while trace amounts of heavy water and rare noble gas isotopes suggested that Borisov's parent system had experienced a different history of stellar nucleosynthesis, possibly including contributions from different types of supernovae or stellar winds than those that enriched the molecular cloud from which our Sun and planets formed. The comet's nucleus, estimated to be roughly 1 kilometer in diameter based on its brightness and the amount of material it was releasing, represented a natural deep freeze sample of the conditions that existed in another stellar system during its own epoch of planetary formation. Unlike meteorites, which preserve information about early solar system chemistry but have been modified by billions of years of cosmic ray exposure and thermal cycling, or even solar system comets, which have experienced multiple passages near the Sun and gradual depletion of their most volatile components. Borisov carried within its frozen structure completely pristine material that had remained at temperatures near absolute zero throughout its interstellar journey. The mystery surrounding Borisov's origins extends beyond its chemical composition to questions about the dynamical processes that ejected it from its parent system and sent it on the millions-year journey that eventually brought it within range of terrestrial telescopes. Computer simulations suggest that planetary formation processes naturally produce populations of small bodies that can be gravitationally scattered by giant planets onto trajectories that exceed their parent system's escape velocity, transforming them from local objects into interstellar wanderers that carry chemical information between stellar neighborhoods. Some models propose that Borisov originated in a stellar system experiencing violent dynamical evolution, perhaps during the late stages of planetary formation when massive planets were still migrating through their birth environments and flinging smaller objects onto chaotic trajectories. Others suggest that close encounters with passing stars or the gravitational influence of dense molecular clouds could have provided the energy necessary to liberate objects like Borisov from their original orbital configurations and launch them into interstellar space. The observational evidence suggests that Borisov has been traveling through the galaxy for an extraordinarily long time, potentially tens of millions of years or more, based on its highly inclined trajectory relative to the galactic plane and its current velocity relative to the local standard of rest that defines the average motion of stars in our galactic neighborhood. During this vast journey, the comet would have experienced exposure to cosmic rays, interstellar magnetic fields, and the dilute gas and dust that fills the space between stars, yet its nucleus appears to have retained its structural integrity and volatile inventory with remarkable fidelity. The implications of studying objects like Borisov extend far beyond the specific details of interstellar chemistry to fundamental questions about how chemical complexity develops and spreads throughout the galaxy over cosmic time. If stellar systems regularly exchange material through gravitational ejection and subsequent capture processes, then the chemical evolution of any given region of galactic space might involve contributions from multiple stellar generations and diverse nucleosynthesis histories, creating a more complex and interconnected picture of cosmic chemical evolution than models based solely on isolated stellar system development would suggest. The isotopic signatures preserved within Borisov's nucleus provide direct constraints on stellar nucleosynthesis models and the range of chemical compositions that characterize planetary formation processes around different types of stars. Every measurement of its gas production rates, dust particle properties, and molecular abundances adds to the growing database of information about how cometary chemistry varies between different stellar environments and what this variation reveals about the physical conditions that existed during the formation epochs of other stellar systems. The technical challenges involved in extracting maximum scientific value from Borisov's passage required pushing observational capabilities to their limits and beyond. Ground-based telescopes equipped with adaptive optics systems worked to minimize atmospheric turbulence effects, while space-based instruments provided the stable viewing conditions necessary for precise spectroscopic measurements of faint molecular emission lines. Coordinated observations across multiple wavelengths allowed researchers to simultaneously monitor different molecular species and understand how the comet's activity varied as it approached and then receded from the sun's warming influence. The discovery and study of interstellar comets like Borisov represents a new frontier in astronomical research that bridges traditional planetary science with galactic astronomy and stellar evolution studies. These objects provide natural laboratories for studying how chemical processes operate under conditions that cannot be replicated in terrestrial experiments, while their trajectories through the solar system offer unique opportunities to study interstellar material using the full range of analytical techniques available to modern astronomy. The broader context of Borisov's visit includes its role as a messenger carrying information about stellar formation processes that occurred in entirely different galactic environments, possibly around stars with different masses, metallicities, or evolutionary histories than our Sun. The chemical signatures it carries represent a form of cosmic archaeology that allows researchers to study the products of stellar nucleosynthesis and planetary formation processes that occurred light years away and millions of years ago, providing direct access to information about cosmic chemical evolution that would otherwise remain forever beyond the reach of human investigation. As Borisov continues its journey away from the Sun and back into